Hello, everyone, and welcome to the sixth session of the Quantum Computing and Cybersecurity Lecture Series and Hackathon. How are you? Kamusta po kayo? I
Okay lang
hope,
po.
uh, so I hope na enjoy nyo po yung mahabang holiday, most especially yung nagdaang Semana Santa. So, right now, we're back at it again for another series of lectures. Now, before we dive into anything else, do you know that World Quantum Week is right around the corner? You heard it right. 3 days to go before the World Quantum Week in the Philippines kicks off. And now for a fun fact. So, 3 days from now, it will be on April 14. And the date April 14 was chosen because of this reason. Now, 4.14 are the first three digits of the Planck constant. That is 4.14 times 10 to the negative 15 electron volt seconds. Now you know it. All right, so before we proceed with our lecture, let us always keep in mind the session rules to make the most out of our activity today. So, first, you have to engage actively. Immerse yourself in this learning experience. Second, be open. So, we're here to have meaningful conversations with one another. And the third one, ask away. There are no dumb questions. Don't hesitate if you have questions brewing in your mind. And finally, respect everyone. You must give the highest level of respect to all who are participating in this activity. Are we all clear with our house rules? Hit the thumbs up button in the comment section. And if you're good to go, great! Oh, so and now see this thumbs up coming in. So before we jump into the heavy quantum stuff, let's do a quick vibe check. Now, on your screen, you should see our mood for today. So on a scale of 1 to 3, are you a number one? You're happy just to survive the week? Or number two, just feeling calm, chill, or just cool? Or number three, absolutely excited for today's session. All right, so let's see the chat. Hmm, parang napaka-diverse yung mga sagot. May 1, 2, 3, no? Napaka-diverse talaga, no? Walang naglalamangan nga maraming 1, maraming 2. Napaka-diverse yung mga sagot, no? Okay, so now, before anything else, uh, I would like to ask you something about your thoughts or experiences so far in the previous session. Can we see some hands over there? Don't be afraid. So, how was your experience, or what are your thoughts in the previous lectures? Walang nagre-raise. So, let's view the chat again. So it looks like baka encrypted yung mga feelings nila. So they remain a secret for now. So, yeah. Uh, so no worries. Let's let's just continue on with our activity as we go through today's topics. So it's hard. It's hard to digest. Muntik akong napakanta doon, ha? Hmm. Muntik akong napakanta pagkabasa ko yung It's Hard. Well, it's okay na. Don't be so hard on yourself. Ano pa? All right, so all right, so I guess parang wala nang share. So, yeah, to warm your brains up before the lecture, I'll now give the floor to my co-host, Mr. Andrew Daniel Corpuz.
Okay, thank you po, Sir Haron. All right, so sino sa inyo gusto mag-warm up? Ay, sandali, hindi ko po pinapakita mukha ko. Ayun. So, sino dito sa inyo gusto mag-warm up? So, emote-emote naman kayo dyan. Ayun. Kita ko ng mga emotes niya. Heart, palakpakan, heart na may star. So, of course. So, ang warm up pala natin for today ay may halong twist. So, sa nakikita nyo, the answer itself is a question. So, for the first answer, ay hindi, sandali, bago muna yan. Bibigyan ko muna kayo ng example kung paano laruin tong warm-up Jeopardy na prepare para sa atin ngayon. So, ganito. So, una ipapakita is, this fundamental unit of quantum information can exist as 0 and 1 or both at the same time. So, yung sasagutin nyo is kung ano dapat i-question sa kanya. So, what is a qubit? Gets na ba? Or kailangan pa ba ng isang example? Actually, wala na pong another example. Ito lang. So, okay, magsa-start na po tayo. So, ready na ba ang lahat? Okay, I'm assuming ready na yan. So, for the first answer, this gate creates superposition from the state ket 0. So, what is the question? Paki-drop lang po sa comment section ano yung sagot niyo para makita natin. What is a Hadamard gate? What is a Hadamard gate? Oh, ayun. Galengs. So the answer is, what is a Hadamard gate? Correct. So for the second one, this algorithm provides a quadratic speedup for unstructured search. Okay, the keyword is unstructured search. Quadratic speedup. So what is the question? What is Grover's algorithm? Ayun! What is Grover's algorithm? Very good! Grabe, may natutunan nga sila the past lecture series weeks. So for the third question, ayun, ito pa yung sagot. So for the third question, this measures and describes how resource usage grows without input size. So what is the question? So waiting. What is big O notation? Hmm, meron pa po ba? Okay. Ano po? What is computational? What is linear complexity? So the answer is, what is time complexity? Okay. Ay, skip na po natin to. So, the date is April 14 pala ngayon, di ba? So, na-mention pa po pala ni Sir Haron kung ano about yung April 14. So, what is the question po dito? The date is April 14. Na-mention po to earlier ni Sir Haron. Yes, what is World Quantum Day? Very good. So, na-explain na po pala ni Sir Haron ano, bakit po World Quantum Day. Dahil po nag-ano po siya sa na number 4.14 which represents the first digits of Planck's constant. And now, naaliw ba ang lahat sa Jeopardy na to? Emote-emote naman. Naaliw lang po ba kayo? Ako. So, natapos na pala natin ang ating warm-up. So, of course, after warm-up, anong ginagawa niyo? Of course, ang ginagawa ko is matulog after warm-up. Pero so my price po ba sa actual Jeopardy ranges from 200 to 1,000, oh wow, $20 to $1,000. Not sure po Sir Harold, wala po pa kasi yung stipend ko. So of course, hindi magiging possible ang learning natin today without our speaker. So without further ado, let me introduce our lecture for today. So introduction is for Sir Edmar. So Sir Edmar, he is a data protection officer at Midway Colleges in Company and a Qiskit advocate, and he is currently pursuing a Master of Science in Data Science at De La Salle University with research interest in privacy-preserving algorithms, higher education data governance, and quantum machine learning. Okay, Sir Edmar, it's time for you to take the floor po, sir.
Hello, good afternoon, everyone. Hello, okay. Just to check. Okay, can you see me? Okay. Okay. So, just to share my screen. So, how's the series? Can I ask a show of hand for those uh who completed the series since the day one? May I ask the show of hand for those who completed the series since the day one? Okay, just to check. Okay. So can you see my screen? Okay, okay. Thank you very much. Um, I'm audible. Am I audible? Okay, okay. So day one lang po na complete. Other days, okay. Okay, sige, sige, sige. So by the way, what happened to my camera? Okay. So sige. I'll close na lang the camera. May problema yata yung camera. Okay, sige, sige. Okay, so I'm Edmore Dizon. So I'm a data protection officer and pursuing data science at the La Salle University. I'm also a Qiskit advocate. So for today's lecture, the title is intentionally. So we're not starting with algorithm. So we are also not starting with code. What we are starting with is qubits. So because in quantum machine learning, it builds on physics, not abstractions. So the focus of this materials is from IBM provided that I am a Qiskit advocate and some series of lectures I attended specially from my mentor, Prof. Dylan. I have modified and expanded it for this kind of avenue. So let's be clear for the beginning, okay? Since some of you haven't continued the series, yung iba putol-putol. So this is not a hype talk. So this is not a promise of quantum supremacy. So for our lecture, what we will do is conceptual and practical computation journey of quantum in machine learning. So at the end, we would like to clarify what quantum machine learning really is and what is not. Okay, so what it exists currently and how tools, okay, especially different tools allow us to explore it responsibly. So by the end of the lecture, all of you would like to clear definition, define the learning objectives. So the goal is not to memorize the quantum algorithm, but the goal is to understand where the quantum computation fits into machine learning. So what role of quantum models play, and would like to emphasize why quantum models or methods is hybrid in current era. So that's why if we finish this lecture and you still believe that quantum machine learning replace classical machine learning, so I'll fail for this lecture. So our goal is to understand the role of quantum computing in machine learning and how these two interact. Okay? So for today, since some of you mentioned na paputol-putol. So we will have a quick quantum foundation review. Okay. Then we will go through, we will learn what is variational quantum algorithm is. Then what is quantum machine learning? And we will discuss two hybrid quantum models in machine learning, which is the QSVM and QNN. Okay? So I hope everyone is clear to our objectives. May I show heart emoji on the screen? Okay? Okay. So very good. So so for to understand quantum machine learning, so we must first understand the existence of quantum computing. Okay, so unlike classical computer, so we use we store information in bits. Okay, so classical bits. So there's two possible outcome for classical bits, either 0 or 1. So for classical machine, so we process information logically, execute operations sequentially, and produce deterministic and single output. But in quantum computing, we produce computing algorithm. Okay. So in machine learning, this doesn't mean quantum computer or faster version. Okay. So we introduce the superposition, entanglement, and quantum interference. So to have an overview, so everyone could see my screen. Okay, so let's have a quick review. So we will review the concept of quantum computing using a quantum platform, what we call the IBM Quantum Composer. So let's begin. So this is a quantum composer. Okay, it's a graphical and browser-based interface which allows us to build quantum circuit visually and simulate quantum computation. So as part of quantum platform, so we can access it in via cloud. Okay, so we can access it via cloud. So okay, so you can access it in quantum.cloud.ibm/composer. So this is used not for programming, but thinking first. So the composer is divided into several regions. So this is the circuit canvas. This is the qubit wires, the gate libraries. This is the visual panels, and the QoS for the codes. So let's start. Let's review for what is qubit. So anyone, so can can anyone in this session would like to share what is qubit? What is your understanding and what's qubit. Okay, so what is qubit? Anyone? So qubit, okay, either 0, 1, or both. Okay, good. So now in computing, so how it will be represented. So a classic bit can only be 0 or 2 state, but now in IBM Composer, okay, so we know that what we will do is we'll represent it in a composer. So we will select a 1 qubit. So this is similar to classical. So how it make qubits different is the randomness. Okay. So unlike classical bit, this representation already hits. So as you mentioned, the qubits can be either 1 or 0. So there's a state of either 1 or 0. However, in qubits, there is a probability. So unlike the classical bit is deterministic, in uh, qubits, there is a probability. Okay. So next concept, the superposition. So in superposition, so I will now apply Hadamard gate, okay, to the qubit, okay. So the Hadamard gate transform the ket 0 into equal superposition. So the ket 1 is 50% probability and ket 2 is 50% probability or either. So as we notice in block sphere, the state from pole to pole, okay, extremely important. The qubit is not half 0 of half 1 because we ensure, so it is an half 0 and half 1. Okay. Then, as you notice, now we will increase the qubit. So let's try to have a 2 qubit. Okay. So let's increase the qubit. So now, after I apply the Hadamard gate for the first qubit, then we increase the qubit. So what did you notice on our state vector? So from kept 1, what happened? The system is now in superposition of 0, 0 and 0, 1. So in notation, so the additional qubit double the size of the state space. So right now we have 4 state space. So this exponential growth is row representation result of quantum machine learning. Now, this state, this quantum, will be essential in machine learning once we introduce this what we call measurement. Okay? So for this, we use the 1025 shot. Now, we address the measure. So what's the measurements doing is we address measurement. So the quantum state collapses and we obtain classical bits. So about 50% of the results are 0, 0, and 50% of the result is 1, 0. Almost 1, 0, the probability. The second concept, third to the last concept that we'd like to introduce is the entanglement. So the entanglement demonstrate the correlations. Okay? So the correlations, so we use the CNOTs to introduce the correlations of qubit 1 to qubit 2. Okay. So we started to introduce the Hadamard gate in qubit 0. Then we introduced the CNOTs gates from qubit 0 to qubit 1. So as we observe, okay, the state of 0 kept 00 and kept 11 appeared. Okay, so there's an entanglement on this. So in qubits in the machine learning, we'd like to introduce that entanglement create features correlations that cannot be factorized. So later, it's important to understand how qubits use in the machine learning. Okay, so this number is the complex number that produced by our quantum computers. Now, the question is how we will use this complex number into classical bits. Okay, so let's move forward. So why we need to review the concept of qubits? Because right now, let us now review. So right now we are currently, it's what we call NISQ era. So which stands for noisy intermediate scale quantum. So this term describes that the current generation of quantum computer is intermediately scale. So means we have tons to a few hundred qubits. So this is not enough to fault tolerant computation. At the same time, this quantum computer is noisy, meaning the quantum states are affected by errors. So their coherence happens quickly and gates are imperfect. So as a result, today's quantum computer cannot wrong run. So their diff circuits is reliably. This is strictly important for quantum machine learning, meaning we need to realize that quantum machine learning today must be hybrid. So there is no machine learning that fully run in a quantum computer. So currently, our quantum machine learning is run by hybrid. So as we go on, so this presentation is promised that currently we have in an NIS era. So meaning for NISQ era, so what we experience right now is our quantum noise or error. So when we say noise, so why noise exists in quantum computing? So first, quantum noise, there's a coherence noise. So this happens when quantum gates are not applied perfectly. For example, there is a rotational gate slightly over rotates or under rotates. So that's why we try to minimize the noise in computing, and we try to incorporate the quantum into machine learning. So to further explain the concept of quantum, so let's first introduce the variational quantum algorithm. So variational quantum algorithm, as I mentioned, is an hybrid quantum classical algorithm which combine the parameterized quantum circuit with classical optimizer. So this is the quantum circuit, and this is the classical optimizer. So BQA is explicitly hybrid. Okay. So the parameterized quantum circuit and classical optimizer. So dalawa siya. Okay? So in quantum device, we prepare the quantum states and we measure the expectation value. In classical computer, we adjust the parameter and decide the next circuit. So on this architecture, we start there's this kind of architecture because of noise. Okay, so the BQA is the backbone of other algorithms such as which we will introduce you in the later slides. So again, in variational quantum algorithm, we there it's a hybrid of quantum compute, parameterized quantum circuits, and classical optimizer. So let's first look at um the what how the quantum algorithms work. So first, so the quantum circuit is prepared in parameter here. Then the circuit is executed on a right now we're doing it in simulator, and measures are collected. Um, then the result is sent to the classical optimizer. Then the parameter is updated. Then the loop repeatedly until convergence. To clarify, in quantum computer, never perform the optimization. So the optimization performed by the classical computer. Again, so now let's discuss the quantum variational quantum circuit. So this is the representation of a variational quantum circuit, but in circuits, so quantum variational quantum circuit is divided uh, into two. Okay, first is the encoder. Second is the answer. Okay, the data encoder maps the input value of quantum states. So for example, in this, we have 4 qubits. So each qubits, there is a rotational gates. Okay, so we encode it via rotational gates. Then determine what quantum state can be represented. So the ansat is the tunable parameter. For example, for this, how we tune the parameters. So we introduce observables and at the same time correlations between each qubits through entanglement. So for example, the qubit 1 is entangled with qubit 3, then qubit 2 entangled with qubit 3, qubit 1 entangled with qubit 2, then qubit 0 entangled with qubit 1. So this entanglement is what we call circular entanglement. We try to look the correlation of each qubits. So as I mentioned, in qubits, there is a relation in these circuits. So we determine the quantum state can be represented. So encoder, what encoders do? So encoder convert the classical data into quantum data. Okay, so it embeds the value into quantum state. So typically it's using rotational gates. Okay, so uh, typically the rotational gates are X gates, the Y gates, and the Z gates. So data can be encoded into phase of quantum states or amplitude of quantum states. Um, it's important to uh, map the encoding, so the encoder is one of the most critical design choice in QML. So its job is to convert the classical data into quantum data. Okay, so the data can after this is after we encoded the classical data, so we now go to ansat. So ansat is a German word for guess. So which is one of the most important and sometimes misunderstood concept in variational quantum algorithm. So when we talk about ansat, so in quantum computing, ansat is the parameterized quantum circuit that represents problems and define the set of states and the algorithm can explore. So ansatz, sometimes called oracle or problem Hamiltonians. So it depends on the context. So in ansat, so we parameterize rotational gates and establish the unitary operation. So that's why we introduced the entanglement as mentioned. So they tune the classical optimizer, meaning if the answer is too simple, it cannot represent the solution. If it's too complex, the noise dominance and training become impossible. So once the circuit was executed, we must we must decide what information to be extracted. So in quantum computer, our expectation, so we measure bits basically in Z basis. So once in many tasks, so what we measures is what the observables, which is commonly the Hamiltonian. So observables determine what information is extracted from the circuits. So how it be implemented in simulation? So observables are derived from molecules or compound structures. In optimization, so Hamiltonians are constructed by Ising models. In machine learning or in QML, Hamiltonian are designed based on the structures. So generally, so this is the generic quantum circuit. The 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 quantum quantum computer does not perform the optimizations. So what the quantum computer do is the quantum circuit runs, measurements are taken, then the results return to classical number. Then once the results are classical, the classical optimizer, either COBLYA or there are other optimizer like SPSA or gradient based method. Then this is tuned and parameterized until we 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 in short we explore the states and classical computer decides what to do next. To There's specific implementations of this algorithm. So in simulation, we introduce is in variational quantum agent solver. In optimization, we use this in Cubo. In machine learning, we introduce it in we use it in quantum neural networks or other hybrid quantum machine models. So as a review, this is the foundation of how the quantum machine learning works. So the classical data is processed in quantum circuits, then the measurement in quantum states will be used for the classical solver, and this is the flow. Now, after we review the quantum variational, let's next review the machine learning. So machine learning is a subfield of artificial intelligence where the rules are inferred from data, like what your exercise earlier. So we determine the questions, okay, from the data. So in visually, we we fed the data and the output in the computer and produce the rules. Okay? So that is machine learning. So machine learning concern patterns from data. So our concern for machine learning is how can the model approximate unknown functions from the data. So we determine the target functions. And the same time, how can parameters so be optimized to minimize errors or loss? We need to accept that in any processing, there is error or loss in processing. So machine learning governed by data representation, optimization, generalization, and inference. So all machine learning, either classical or quantum, starts with data, regardless of image, text, signals, or table. So this data is represented as vectors. Okay? In classical machine learning, these vectors uh, is revalued in space. So what happened is we determine the target functions and represent it into vectors. So what is the process of these target functions? So what happened to to machine learning pipeline? This is the general machine learning pipeline. The data start with data sets. We will split the data sets into two, the train and the test sets. Then we train the model. Okay. Then we generate the prediction and we evaluate the performance. So this pipeline remain intact as we introduce quantum machine learning. So it will not remove the trains test, split, and the cross-validation. So again, this is the generic pipeline of machine learning. So from the data that we have, we split it into two, the train and test. So what is the distribution of data set? So usually in processing, uh, train set is 70% of your total data sets, and test set is the 30% of your data sets. So our goal, as I mentioned, our goal is once we process the data, so this vector is stored into a bits, so either 0, 1. So now, in classical machine learning, we operate the vectors as real numbers. Okay? So we represent it as Rn. So now, what if this number is operated in Hilbert space? So this is would like to clarify the what quantum machine learning is. So we try to represent our data into quantum space, which is the Hilbert space. Data still at vectors, this data is still in classical, but once encoded, it represents the quantum states. So in representation, your model is no longer a functions or a neural graph. So instead, it become a parameterized quantum circuits that involves states according to quantum mechanics. So this briefly define how quantum computing interrelate with machine learning. So we try to represent the data in a quantum states. So in definition, so quantum machine learning is a hybrid approach in which quantum computing completely classical machine learning workflow mostly opened by applying quantum algorithms to classical data within quantum classical training loops. So as I mentioned, in current era, we using the hybrid implementation in quantum machine learning. So we use the quantum computers or simulators to represent the data in a Hilbert space, then do the optimizations or the optimizers in classical computer. So when we talk about quantum machine learning, so we're not replacing machine learning. We're we're representing the data in the Hilbert space. Okay? We're not introducing that quantum is faster or quantum is superior. We're trying instead quantum computation, which is used in machine learning workflow. We mean that our goal remain learning from the data. Classical ML concepts still apply. Only specific component was the replacement of quantum process. So therefore, quantum machine learning is integrative, not disruptive. Okay, so we're not introducing that quantum machine learning is faster or quantum machine learning is superior. So we're just looking represent the data in the quantum states. Okay. So as we transition, so why we need to clarify this Hilbert space. So Hilbert space is a complex vector space. So the data as represented in Composer earlier exponentially large with respect to number of qubits. So what we're trying to do is we try to determine show that in classical computing, there's still a data encoding. In quantum, there's still data encoding. The quantum state evolve. We use the quantum measurement. Then in classical, we still use the loss computation. We use the gradient parameters updates. We still use the training loops and the evaluation. So in quantum machine learning, we keep the entire ML pipeline intact. The only thing that changed is how the feature is processed internally. Okay, so this is the hybrid QML design. So right now, the current QML trends in research. So what we see is the computer vision mostly use this approach. So across literature, the parameterized circuits uh, is still where this represent how many research is using quantum machine learning, mostly in computer visions. Okay. And some of the field is network communication and IT. There are also the use of quantum machine learning in health and space techs and remote sensing. Then, which hardware do the QML application? So right now, as mentioned, uh, we use the G. Right now, we're using GPUs and CPUs to process QML, mostly in health. Okay, so hardware. So it depends on the task. So QML models run either in quantum simulator, either in GPU or CPU. We are rarely using machine learning in real quantum processing units. So the factors why is because there's an influence of noise level or circuits or number of qubits. So currently, most QML research is trained on simulator and validates on small CPUs, QPUs. So as mentioned, we using simulators. So we'd like to introduce to you a tool that currently using in ML, which is the Qiskets. So Qiskit already discussed on some of the series. So how the this simulator process in quantum machine learning. So the user writes the quantum program. So the program submitted to Qiskit runtime. Then the program sent to in the clouds. So translate into false sequence, then execute the processor. So currently we can do the processing of do the quantum machine learning through uh, these tools. So Qiskit. So I int- Qiskit is not a single tool. It is a collection of software for working with quantum computer. So this is the pattern how the Qiskit uh, do the algorithm. So the map, we first map the problems, then when you say map, we translate the problems into quantum circuits or operators. Then we optimize, we adopt circuits for target hardwares. Our target hardwares right now we're using the GPUs or CPUs. So we lay out the optimizations. So we execute the Qiskit runtime, and we process it. So this pattern is appeared later on. We introduced the QSPM and QNN. So in summary, so not all quantum algorithms are suitable uh, for machine learning. So because of the noise or the so small algorithms sometimes perform well on simulator. So others are unstable on real hardware. But right now, so uh, quantum simulator, so there's an annealers, there are analog computers, but currently digital quantum computers are mostly applicable for all of the algorithms. So other are designed specifically for NISQS devices. So algorithms choice must be matched for hardware applicability. So for our task for now, so we're using uh, For digital computers, we can use the variational quantum circuits or some application specifics. So after we have an overview of variational quantum algorithm and machine learning and hardware, so let's now introduce the one of the machine model, which is the quantum support vector. So quantum, as before we proceed with quantum support vector, let's first have an idea of support vector SVM. So first, let us understand what is classical support vector is. So quantum support vector machine is a supervised learning algorithm which is used to used for classification and regression. So the core idea of SVM is geometric. Usually in machine learning, we try to draw a line to separate one variables to other one factors to one factors. For example, we have 4 blue dots on the left and 3x dots on the right. So in machine learning, we try to draw a line to separate which are blue, which are red, or which are dots, which are X. What if our data is blue, blue, X, X, blue, blue? Okay. So now what we're trying to do is we try the not to see or not to look the data into a not linearity. So we try to look the data in a different uh of we tried in we introduce a higher dimension to separate the blue dots and the X dots. So for example, this is the data sets. So what we trying to do in SBM is we try to find a decision boundary, so-called hyperplane, to best separate the data point from different class. So this boundary maximize the margin of distance between classes. So we try to rotate from this plane into this plane. We introduce a new dimension. So currently, this is a 2D dimension, the X and Y. However, in the introductions of new features, a new dimension, we can now separate the blue dots and red dots. So this separation is what we call, we determine the kernel functions. So this is the kernel trick. So what we trying to do is this kernel tricks allow SBM to model the complex boundary. So to avoid this higher dimension. So we introduce this higher dimension. So in quantum computer, so naturally operates in high dimensional space. So that's why we introduced the kerneling. So kernel evaluation is a natural candidates for a in quantum computers. So on this slides, so classical kernels, so the power of SBM lies on representing the data. So what will be the algorithm of SBM? So we tried, we in classical SVM, the feature map is explicit. So we encode the data. So what we're doing is we compute the kernel matrix through the Langarian dual form. So the algorithm then solve the Langarian dual form and predict the class level. So now, what if this data, as we mentioned, the vectors data, we represent it into quantum, in quantum. So from this architecture, what we do is the data encoded as vector, we introduce it, we encode it, the classical data, then we use the quantum encoding to map the data into quantum states. Then we compute the kernel matrix using the quantum computer. Then we solve the Langarian dual problems classically and predict the class. So this introduced the division of labor, as I mentioned earlier. So the role of quantum computer is to prepare the quantum feature map and evaluate the kernel value. Then the classical computer is responsible for optimization and training prediction. So this separation prevents the misconceptions that quantum computer does not decide class level. So on this level, so the quantum computer try to answer questions, how similar are these data points? So quantum support vector machine is a quantum extension of SBM. So what we're doing is we represent the data. Okay. So in quantum state, we determine the similar computation in quantum, but the optimization and the decision rule is we use the classical computer. So in QSPM, what changed is how the feature are represented, not how the classifier is optimized. So in QSBM, the classical data is encoded in quantum states using quantum circuits. Then this circuits acts as a quantum feature map. So the superposition and entanglement, this is how the work of superposition and entanglement. So in classical computing, we do the feature engineering, but in quantum machine learning, this replaced the classical feature engineering with quantum state preparation. So the kernel is estimated. So what happened is each kernels, so the circuits, each kernels, after uh, each features will be uh, encoded in circuits. So as a rotational gates, and uh, we represent it into a ZZ feature maps. So, for example, we have 2 qubits and 2 features. So the features is encoded in first data point as a quantum states, then encoded into second data points in another quantum states. So what happened here is the quantum hardware, we try to compute the overlapping interface and the measurements at the end. So in QSBM, the quantum feature map, so the data encoded as a vector, the classical data, we apply the quantum feature map to evaluate the quantum kernels matrix on a computer. Then, this quantum matrix, we solve the classical SBM using the Langor, and we predict the label. So what happened is the SBM, we introduced the SBM using in this part. So now let's move to the next model, which is the quantum neural networks. Before introducing quantum neural networks, we revisit the classical artificial neural networks. So what we do in classical neural networks, so on the left, so we a single artificial networks. So what we do, this is the single artificial networks. And on the right is the multi-layer neural networks. So what happened is we have inputs, and each inputs we introduce a weights. So the summation of each weights, then we use the activation functions as an output. So this is the we perform the linear combinations of inputs. Then this singular inputs was uh, introduced to each hidden layers. So the hidden layers perform the learn transformations. So each weights. So after that, there will be a final output. So every connection has a weight, and every connection is trainable. So the neural networks is just many neurals stacked in a connected layer. So now each layer performs uh, hierarchically. So what happened is, okay, so we introduce how the learnings do in this so in forward pass, so what we do is we pass through all data forwards, so until we determine the loss functions. Then we compare the predicted output in a true level. Then to to optimize it, so we use the chain rule to apply for this layer. So when we say chain rule, so we determine uh, the derivatives. So what happened on this is we used a chain rule applied for this layer. So we compute the gradients of each loss. Then we updates the weights. Then repeat the many iterations. So the learning in in artificial neural networks happens by error propagations of back propagations, and we update the weights. So how we will represent this in a QML? So QML is not magic. So we tried, we not replacing the classical machine learning. So QML is hybrid design. So let's now introduce the parametric quantum gates. So what is the parametric quantum gates are the rotational gates. The core of QNN is the parameters. So we use the adjustable weights. So the quantum states in QNN, this is the generic QNN architecture. So in QNN, it's contained of data encoding layer. Then we introduce one or more parameterized quantum layer and the measure stage. So the output is a classical value of probability and expectation value. So this value is fed into loss function and classical optimizer. Then the loops repeats. So structurally, it mirrors the neural networks. So in quantum, this is the full parametric circuits. So in quantum, we encode the data, the classical data. Then the circuit act as encoded data. From this, so the learning happen in adjusting the parameters to minimize the quantum loss functions. And okay, so let's first introduce the unitary parameters. So the unitary parameters are represented by the rotational gates. So N denotes the number of qubits required. So for example, and M defines the structure of trainable parameters. So the features is the rotational gates are trainable. So in quantum neural networks, the UU is the model. Unlike in neural networks, classical neural networks, weights is multiply inputs. But here, the parameter rotates the quantum states. The NN, or the N, determine the dimensionality of Hilliard space. So the number of encoded features determine the number or the size of quantum space or number of qubits required. And M determine the number of layers or the number of rotational per qubits. Sometimes the number of trainable parameters is larger than the number of qubits. So this happens when QNN is embedded in a hybrid classical quantum architecture. So through this, we use intermediate layer as a larger model. So what we do is the common components remain identical, but the parameterized routinary, the trainable rotation. So what changed is the QNN output may fed in another classical layer or a combination. So let's start with the architecture. So we focus on data encoding. So what happened, the classical data in neural networks is input into weights, by weights, then passed through to activation. In QNN, classical data is encoded into quantum states. So often through rotational gates. So this step determine which dimensions of quantum stage is explored, either X, Y, or Z. So for encoding leads to ununiform quantum states or no learning. So therefore, encoding is a trivial process. So but we try to design this decision. So the weights, the parameterized circuits. So unlike classical neural networks, in QNN, we do not compute weight sum. Instead, we the trainable parameters are embedded in the gates angles. These angles transform the quantum states, which affects the weights is nonlinear or cross-global the quantum system. A single parameter's change can affect all amplitude. Uh, so this training, so we introduce entanglement. So we try to so in okay, we introduce the entanglement. So so how we train the QNN? So it happens through answer line on expectations value. So entanglement introduce the quantum correlations. So across states, these correlations play a role similar to like weight sharing. So we try to introduce include we use entanglement to for quantum correlation. So for example, we we use entanglement in qubit 1 and qubit 2, then qubit 2 to qubit 3 and qubit 3 to qubit 4, then qubit 1 to qubit 4. So this entanglement is what we call circular entanglement. Then, okay, so the measurement gates. So in quantum, we must measure the systems. So after we uh, we do the training parameter entanglement, so measurement act as a decoder. So this is the output layer of QNN. So usually measurement is done in Z. So however, other measurement schemes are possible, like custom Hamiltonian or extract enriched information. Now, in artificial neural networks, we do backpropagation, but in to adjust the weights. But in quantum computer, there are other methods, but the most applicable available right now, which the hardware can can process, is the parameter ship rule. So in parameter ship rule, so uh, what we do is it's a method that compute the exact gradients in physical. Then once we train the parameters, we evaluate the circuit twice in positive shift, then negative shift. Then the gradients is then compute, and as a result, the result is exact. So this is the valid common quantum gates. So this use uh to evaluate the optimizer, either it is the softmax or cross entropy. Softmax for multiple classification, then cross entropy if binary. So we introduce the architectures of the quantum machine learning. Now, as a use cases, so this is a hybrid uh, quantum support vector is a use cases currently. So this is a study of a data sets in educational data, a psychological data. So what we did is we trained the data, okay? So we use the classical pre-processing to determine the features and normalizations. Then we encoded in a simulator. So a quantum feature map was generated. Then this quantum feature map was evaluated through its kernel. Then we produced the kernel matrix. Uh, by the way, never mind the pink one. Then this kernel matrix, the outputs of its measure was used. We used the classical SBM to train the the model. Then we do the prediction. So another example is it is QNN. So the same data sets. So we process the classical pre-processing of the data sets. Then we encode it in quantum computing. So the parameterized circuits. So we use the variational quantum circuits. We compute the loss computations. Then uh, we use the parameter shifts to determine. Then we do we produce. This is the sample architectures currently we use. So what actually changed? So in variational quantum circuit, so what happened is the circuit parameter in QSBM, we try to introduce the feature map circuits, and in QNN, we try to introduce the parameter. So to learn more about quantum machine learning, so this is a QR code. So in the right one is the Quantum Machine Learning Foundation. Then the right one is the sample kit implementation in you can use Google Colab to to practice the simulations and using Qiskits. Okay, so what I want to leave you is final takeaways. Quantum machine learning, it is not a replacement of classical machine learning. So it is a research driven. So we try to introduce a hybrid extensions of data machine learning. So uh, we need to use responsible this tool, and we see the potentials of introducing uh of these applications. Okay, so uh anyone I did so so there's a question, by seeing the circuit, how we identify entanglement. Okay, so by the way, seeing the circuits, so I'd like to show the example here. here. So there's a questions in how we determine the entanglement. So this is a sample circuits in quantum kernels. So what we do is we introduce the Hadamard gates here. Then in UI we use the rotational gates. So we introduce entanglement. We try to the correlations of qubit 1 and qubit 2. Then so far and so forth. Okay. So again, that's uh that ends our topic for today. For this session, for this topic. Okay. Do you have any question? Okay. Why is it possible for isn't possible for quantum to optimize and we need to delegate the work to classical? Good question, Pinela. So as we introduced earlier, so we are our quantum hardware right now is in have a noise. So since quantum computer is sensitive for noise, uh, um, what we're trying to do right now in machine learning, so we we need to accept that there's a noise. Okay, so um, in we tried in quantum computing. So the quantum computing is a different space. So we have the Hilbert space. So what we try is to process first the data into quantum space, then produce the measures into classical data, then these measures will be used in uh, knowing the optimizations of the machine model. However, there's a separate algorithm which will be discussed by the next topic about optimizations. So right now, what I introduced to you is the introduction of hybrid quantum and classical machine learning. Yeah, thank you, Fennery. So measurements collapse the quantum. Okay, thanks po. So right now, in our NIQS era, so we need to accept that machine learning is can be processed uh in this setup. Okay. Uh, do you have further questions? None? Sir, yes, Pinelli, Safe.
Ay, ayan.
So,
Ay,
by the way, is this possible for us to have a full quantum hardware? Okay, Pinelli. So, by the way, so wait. Okay. So, to answer that, uh, okay. So, there's a question. Uh, is it possible po ba that for us to use a full quantum hardware? Right now, we need to accept the current uh, uh, okay. So right now we are in NISQ era. So which is the noise intermediates uh, s- uh, yung errors natin. So quantum errors. So we hope that in the future, okay, So right now there are fault tolerance and error corrections. So we hope that in the future, however, since quantum computers right now, the materials for computer is scarce. Um, I cannot guarantee that we can do the full implementation. Okay. But right now the value or the beauty of what we have right now, all of the experiment or quantum computing, we can do it in uh, hybrid setup. So using simulators or like Qiskits or other tools like Kubo or Penelings. But right now, the quantum machine learning is we separate the quantum state processing in quantum computing, then the classical machine learning in classical computer. Okay. Yeah. Yes. Yes, Pinela. Yeah. Um, but the beauty is we have right now. Okay. So none. Okay. If none, okay. So thank you very much. So yes. So we can have break now until 5:35 if you have further questions. Okay. If you have other questions, so this QR code can be the QR code I uh shared with you earlier is a good material.
So, thank you pala Sir Edmar. Grabe pala, ang dami nating natutunan today. So, before we continue, let's take muna a quick break lang. So, until 5:35, stretch muna, magtubig kayo, CR break. Bahala na kayo kung ano yung piliin niyo dyan. Just make sure to be back on time ha, kasi we'll continue right after. Thank you po. So, okay, nakapag-break na ba lahat? Naka-CR break na ba kayo or water break? So, we'll be moving on na sa ating continuation. But before we start, we'd like to introduce Sir Dylan Josh Lopez. So, Engineer Dylan Josh Domingo Lopez is a PhD candidate in electrical engineering at Chung Yuan Christian University, Taiwan, specializing in quantum machine learning, optimization theory, and data-driven applications for power systems and civic platforms. He currently serves as the director for the partnership and collaborations at the Quantum Computing Society of the Philippines and is a co-founder of the Post-Quantum Technologies in company. In addition, Sir Dylan teaches quantum computing part-time at De La Salle University, Manila. So let's all welcome Sir Dylan.
Hello, I think I have my audio ready. Okay, let me just try to access my screen. Hold on for a minute. Wait. So I'm having a bit of a trouble with my file. Just hold on. Give me 2 minutes. Sorry. Okay, I'll be right back. All right. Okay. So I just want to clarify if you can see my screen and you hear me properly. Right, great. Okay, so thank you. Thank you for staying up to this last part for today. So we're going to talk about quantum computing optimization. So if you are interested a bit on what happened with quantum machine learning, quantum optimization is a bit similar in that sense. Now, if you're interested in, for example, finding the best configuration of things, finding the best options or recommendations for maximizing profit, minimizing cost. This might be something for you, right? So we're gonna go through with several items to discuss. Before we get to quantum computing optimization, I know that you already know about quantum computing, but let's talk about optimization as well. So, what's in store for today is that we're going to talk about optimization theory. So, what are the optimization problems that we have? What are the optimization techniques? How difficult are these optimization problems? And why do we actually need quantum computing for this? Why not just use a regular computer, just like with, for example, with AI and other examples? So, how do we look at it as a pure quantum and pure classical, or even a hybrid of both? Then we're going to talk about what are the quantum computing techniques that we need to we can use when we want to optimize or do optimization. Then, oops, sorry, the last part is a case study, but we're not going to work with a traveling salesman problem, but instead we're going to work with the knapsack problem, a bit more fun, I believe, right? So don't worry about that, and let's go here in the first part. So let's talk about classical optimization. So just for a room check, anyone here already is familiar with optimization theory or any optimization techniques? Let me just see here in the chat. Anyone here or raise your hand if you are familiar with optimization in general. Oh no, very few, no. So only few. Okay. One, two, three. That's completely fine. So this sets the mood on how we're going to discuss today. Now, optimization theory is discussed in several programs, I believe, in computer science, mathematics, and in industrial engineering. But I think there is a rise of interest in optimization theory when you work with mathematical artificial intelligence. For example, when you want to look into how do we perform optimization, gradient optimization, that's part of it. But more specifically, let's look at it in the general sense. So, what does it really mean to be optimized? Okay, anyone here or want to express when you hear optimized, what what comes to your mind? What do you think of when we say, "I want this to be optimized"? Okay, uh, maximum efficient, the best solution. Cool, that those are right terms, and please remember them that these terms define how do we perceive optimization. Okay, so in a very very easy terminology, optimization is finding the best way of doing something. So it is a bit subjective and relative what is the best. So we need to define that. And what is something? So that something is it could be a configuration, it could be a suggestion, it could be an array of things, a vector. All of those are parts of optimization. So let's try to find what is the best option. So, in a more a formal sense, optimization is the mathematical discipline of finding the best solution to a problem. Now, this is by finding that solution in a feasible search space. So, the best way, or the quote unquote best solution, it could be finding the maxima or minimum of a value of a function subject to constraints. Okay, these are limitations of a problem. Okay, then we are provided we have limited resources, and there should be a measurable quality for candidate solutions or these options. Okay, now you might also think that this is highly mathematical. It is. However, these are very interesting mathematics because it translates human language into how machines could make things more efficient. So if you remember back in senior high school or high school, wherein you have worded problems like that like John is 5 years younger than for example Alice. Those are the similar problems that we see in optimization or creating optimization models. Is translating these real world statements into mathematical statements and later on things that could be solved by a regular computer. Okay. So in optimization, we always need a problem. Why do we need to be optimized? So for example, you have a traveling salesman problem. The problem here is how do we get or visit all of the cities in, for example, in Manila, or not Manila, in the Luzon, in Visayas or Mindanao, or in the United States. Okay. How do we visit all of those cities with the least amount of gas because oil prices are really high right now? Or how can we fit all of the things that we need in a certain space, but so that we can deliver it more efficiently? The objective in every optimization problem is that how we can say it is optimized. It could be a minimization technique or a maximization. So it could be based on, for example, distance. We want to minimize distance because that correlates to the mileage of our vehicles. Or it could be minimization of space that will occupy our container. Then lastly is there is a method. How can we be optimized? So that's a question. What are those things? So we're going to talk about that in the next few slides. So just to clear some terminologies, so we have an optimization problem and we have an optimization model. An optimization problem is that given all of the feasible solutions, which would be the best? Best satisfies your objective or the goal. Okay, that is the problem. While these are all of the expressions, all of the mathematical, or sorry, not the mathematical parts, but the given problem that we have right now. The optimization model is the mathematical representation of the real world, okay, or the decisions that you want to make, all of the considerations that you want to make. So, for example, if I want to restrict my diet by, or rather, may restrict my budget in spending, then I have certain rules. Like I could only spend a maximum of 1,000 pesos, 200 pesos per day, but I need to allocate budget for transportation or lunch money. So those things, those considerations could be translated to mathematics. So again, here in our problem, we need to define things that, that efficiently translate what we want in the real world. One, we need the objective function. What do we really want to do? Are we minimizing something? Are we maximizing something? Okay. Next, we need to identify what are the decision variables. What are the things that we need to change, or what are the options that we can just select? And how can we put that into the problem? How can we select them? Or which are those that we need to select? Then we need to define constraints. What are the limits of the problem? Okay. So, for example, what is the maximum budget spending I could have, or what is the minimum budget spending I need to do? Okay. So, in this case, okay, in our optimization problem, we would write it here normally as define the minimization function or define the objective function. What are the constraints given the variables that we need to identify or solve. But in planning that, we need to know what are the knowns and unknowns. What are the logistics that we have right now? What are the realities of our options? Then we need to identify the business goal or the engineering goal or generally the problem that we want to do. Okay. Then lastly, then we apply the limits. Okay. Because the problem itself, the goal could be achieved as it stands. Then while you add more considerations, the problem becomes tighter, okay, because you are adding more considerations. And that's okay. If you want to just solve just a certain number of considerations, that's fine, okay? And you can increasingly add those until you get an answer that satisfies the problem. So, for example, here, if my objective is to minimize something, I need to look at a certain space. So, we have what we call a feasible region. The feasible region is all of the possible combinations of my decision variables that gives me valid answers. Okay, valid answers. So let's say I have two decision variables, y and x, okay? And they could be in the realm of positive real numbers. And all of these lines, okay, could be considered constraints. That, for example, the value of x and y should only be between k1 and k2. So it's in the middle, okay? Should be just in the middle right here, and that the value should be around here below this curve. Okay, this quadratic curve right here should be below that curve, and it should be above this other quadratic curve. Now, if we look at all of those considerations, it actually gives us a colored space. And that space, okay, wherein they should be just or satisfies all of them is the feasible region. Now we want to find the answer there. Okay, it could be the minimum value or the maximum value within this feasible region. So how do we do this optimization? We can do it constraint having the constraints here, or unconstrained. We just allow everything and let the objective function do it. Or sometimes we call this with penalties or soft constraints. So we can add weights on how important these considerations are. For example, I could violate at some times my maximum budget limit of, let's say, 500 pesos a day until 1,000 pesos. That's okay. Then that is like a customized constraint that could be phrased as part of an unconstrained problem. Now, we can also characterize these problems based on the objective function and the decision variables that we have. So we can tell that they could be linear or a linear problem. They could be a quadratic problem, a nonlinear problem, an integer problem, and a mixed integer problem that could be linear or nonlinear. Okay, let's go through some of them. Sorry, yeah. So linear problem is that we're just finding values using a linear function, for example. A quadratic function is that our decision variables now are in powers of two. They could be multiplied to themselves or multiplied to other decision variables. They become quadratic in a sense. Nonlinear is that, for example, our objective function, well, it's not a line. It could be also quadratic. It could be a parabola. It could be a sine wave, or it could be an exponential function. Essentially, it's not a line. It's not creating just a single line. An integer problem is that the values that we're trying to solve is strictly integers. It could be 0, 1, 2, 3, 4, 5, positive 1 to negative infinity of integers. Okay, there could not be, okay, any float values. There will be no 3.14, 7.19, all of those, just strictly integers. Mixed integer is that they have a mix of continuous variables. That could be float values and integers at the same time. But let's talk about nonlinear model. So in those nonlinear models, again, we have linear models wherein they just form a line. Okay, the constraints form a line, the objectives form a line. Okay, what's nonlinear is that, for example, we multiply two variables or that we have a transcendental function. Okay, so the feasible space might look like this. So the progression of the values move in a linear fashion. Now, there are nonlinear models that could be quadratic in nature or polynomial in nature, or they could be nonlinear generally nonlinear in nature. So, for example, quadratic models that the objective function is quadratic, or that the feasible space looks like this. Okay, it could be that the feasible space has quadratic movement. So, for example, here you can see that there are folds or quadratic folds at the end, or that there is a quadratic constraint. That means it looks like this. There are cuts at this side, or the cuts are also quadratic. Okay, so these are considered quadratic models as well. There are also higher order models or polynomials wherein they are formed in different interactions. For example, here the powers of 3. That means there are interactions of 3x's at the same time, or xyz, or a combination of them. Okay, so the maximum value here is around x cube and z cube. So they are still these are cubic in natures, but they are generally considered higher order models. So it could also be higher order models because of their constraints, such as these. And generally, there are very weird nonlinear models. For example, we have a cos y cos x, or cosine y cosine x space wherein we want to minimize that, or it just looks like this. Okay, this is a very nonlinear model. There we have a flat plane right here, and suddenly we have a quadratic space here above in your feasible space or feasible region. Or again, it could be using nonlinearity by constraints. For example, we have an elliptical constraint or a circular constraint, or it could be that it is by quadrants that is considered nonlinear in this sense. Okay. So if we look at the complexity of these problems, so if they are linear in nature, they are lower orders. So it is quite easy for classical computers to solve, or general algorithms to solve. Now, as we increase that, so there is a degree, there are increasing there's increase, decrease in the convexity and increase of the number of local minima. So there are many trap holes, okay? And there are too many options as well. So that becomes a lot more complex. If you recall your complexity theory in the next from the previous days, if you increase the number of your variables and the computation time becomes, well, exponential, then we don't want that. And that exists in several optimization problems, such as nonlinear problems, mixed integer quadratic problems, and of course, generally mixed integer nonlinear problems. Okay, so these are very hard problems right here in the upper corner. Okay, so why is this important now in quantum? So since there are problems that quantum could solve, some of these problems right here are applicable to quantum. And I'm saying every problem, only some, and they are case-to-case bases. So let's talk about some of the techniques that could solve these problems. So normally the traditional methods are the simplex method and the branch and bound methods. These are, what are usually used in all the solvers, okay, out there using your regular computers, or you can use it, you can solve it by hand. So normally these are the techniques used in school, okay. There's also gradient-based optimization, wherein we take the derivative of every step, or generally the derivative of a function, and find its minima, or the minimal value. So these are widely used in machine learning because the objective functions in machine learning should always be differentiable, so that we can perform this, for example, gradient optimization or batch gradient optimization every time we do AI. Okay. There's also other types of optimizations. For example, we have Bayesian-based optimization, or BO, wherein we use probabilistic surrogates. Okay, and we're not going to dwell to that. But anyway, if you're interested, yes, these also exist in solving nonlinear optimization problems. Okay. Then there are very famous ones such as meteoristic-based optimization. So these are the ones using genetic algorithms, evolutionary programming, particle swarm optimization, or generally swarm intelligence. There is annealing-based or thermal annealing, for example, or simulated annealing, or there are biological-based such as ant colony optimization. There are gray wolf optimization, slime mold optimization. Those are considered in biological aspects. And these biomimicry, or in environment mimicry of optimization, could be solved, or could be used to solve nonlinear models. Okay. So if you have used some of these, that's great. You have some idea of how nonlinear models work and what are the pitfalls or the local minima if we have given a feasible region. So advantages, oh, sorry, no, just skip that. So look at the summary right here. So given the type of model, there are some methods that are really good. So for example, in the linear programming, or linear models, or mixed linear models, simplex and branch and bound are still really good at these. But if we add a bit of nonlinearity already, they are not really that good anymore. So for example, with quadratic programming until nonlinear programming, there we now can see, we can now look at other options such as gradient optimization, Bayesian optimization, and meta heuristics. And there would be now other optimization techniques that we're going to be familiar with, which would be quantum optimization. Now, where does this lie? Some would say that it is under meta heuristics. If we are simulating quantum optimization, it may fall in meta heuristics because these are physics-based optimization. But in and of itself, quantum optimization in the purest form using quantum computers is a new category wherein it solves specific problems in the bounded quantum space, okay, or the BQP. So in the BQP, or the bounded quantum space, if you remember, these are only for quantum applicable problems. Now, what are these problems? So these are normally mixed integer quadratic programs, or MIQP. Okay, so these parts right here, given that our quadratic variables are only in binary. Okay, so if we have those, then it is actually applicable to do it in quantum. So, for example, this would be a combinatorial optimization problem, or some call it the integer 1, 0 problem, because we only have one type of binary decision variable, which is decision variable, which is only a binary. So it's either 1 or 0. It's like a choosing problem. Okay, so these combinatorial problems are NP hard. I hope you recall that. So these are NP hard. So classical optimizers will take some time to solve that, but quantum optimizers could help in solving these, right? So what are combinatorial optimization problems? There are a lot. For example, traveling salesman problem is a combinatorial optimization problem wherein we need to choose paths. Routing problem, just like in networks, is also similar to TSP actually, wherein we choose path or the shortest path towards somewhere. Okay. So, oops. So what else do we have? We do have switching problems, relays. That's one. There's also choosing problems, asset placement problems. All of those are considered combinatorial optimization. Scheduling problems as well are considered combinatorial in nature. So hence we can use them or try them out in using quantum computers. So let's talk about quantum computing, okay, or quantum computing and optimization. So we're going to transition a bit. How really, how does quantum computers do optimization? So let's try to recall in physics that there is the principle of minimum energy, that objects would tend to find the minimum energy at any state it would be. For example, in the first law of physics, that if any object is at rest, it will remain at rest. Okay, so given that case, that if it is in rest already, it will not find any more higher energy potential at that space unless there is an external force acting on it. Okay, or that if any object is placed in a higher place, given external forces, it would fall down to the lowest energy that it could get to. Okay, which would be at rest. Okay, whatever it goes, and that will also be applicable into with other cases, for example, convection currents. These phenomena, they would always fall to for the minimum energy that it could be in that certain scenario. So that exists again with thermodynamics. Okay, so given that these are your energy levels, your particles or your systems would tend to fall into these minimum energies. Okay, so for example, there are local energy minima here and global energy. They tend to fall into those places naturally because of nature. Actually, it's because of quantum mechanics. Actually, and this, for example, in temperature, any object that if you try to increase its temperature, it would eventually fall into the room temperature because of thermodynamics. Okay, and are also given its material. And in that case, it still finds its minimum energy at any point. So this is actually similar to the idea in optimization, especially with one in gradient optimization, if we could find it in the principle of minimum energy. So that means in this physical problem, we can consider it as an objective function in optimization, just really taking advantage of nature. So let's try to look at these aspects. Okay, so in physics, the principle of minimum energy is based on energy, of course. And if we try to recall your physics class, we have this general energy formula wherein we have 1/mv² plus mgh. Let's talk about that later. In quantum mechanics, we have this equation. This is the Schrodinger's equation, the very simple one. Okay, this is not the highly complex Schrodinger's equation. And just important here, there's E. Okay, that's the energy part. So it's your time-independent Schrodinger's equation. But the original Schrodinger's equation might look like this with the time-dependent one, but this is in the single dimension. So if we try to look at it in a more general sense, just for you understanding the surface level of how these energies would work into optimization. In classical mechanics, we can just divide it with kinetics and potential. The energy that is moving and the energy that is not, okay, or it could be. So that's your kinetic energy right here, and this is your potential energy if you remember your physics. Now, in quantum mechanics, in the Schrodinger's equation, there is a similar concern. So Kinetic energy is really just this part, and the energy potential is right here. Just for you to understand that these general ideas would still exist. Okay. And now we want to find the minimum energy from here. Okay. Always remember that these are kinetic and there's potential. So here, right, from trying to solve this time-independent Schrodinger's equation, we can have this general equation right here. That means there is some E given a quantum system. If you remember your first lesson, this is a quantum system that is equal to this energy component, okay? This energy right here that includes your kinetic energy and potential energy acting on a quantum system. That's just it. So that means that there is some scalar applied, or the scalar of a quantum system equivalent to the characteristic of your energy movement right here acting upon your quantum system. That's the very gist of the Schrodinger's equation, the quantum mechanical aspects of your energy. And we call this the Hamiltonian operator. Okay. So we can just, oh, sorry, operator. Yeah, that's correct. So the Hamiltonian operator right here acts upon your quantum system. And this operator, we know that it is an operation. And given that it's an operation, it's something that we can encode as a quantum circuit. So we can simulate this. Okay. So this Hamiltonian is the characteristic of energy of your okay of your quantum system right here. So there's another thing right here. Now, E is a scalar, H is an operation. If we know that since it's an operator operation, it is a matrix. So this actually gives you an idea that there is some representative scalar equivalent acting upon the system. There is an equivalent vector onto it. So this is actually just really solving your quantum, your eigenvalues and eigenvectors. Okay, so that's one idea. Okay, so there is a tool for you to work on if you want to find this Hamiltonian. So one of which is the Ising model. So the Ising model is more of a ferromagnetic, so it's on in magnetism and iron, and this looks at the particles or charges in a material. Okay, and imagine that all of these intersections, okay, are particles, okay, and we want to arrange them, and we call this our whole arrangement as the Hamiltonian, by the way, okay. We want to arrange them so that they'll have the minimum energy, which is E right here. So what values of these H, of this matrix, would give us the lowest value of your scalar right here? So these will only have two values, spin up or spin down, up or down. So that's technically a binary problem. So if it's up or down, we want to find which combination of all of those up and downs of particles so that they'll give you the minimum energy. And in nature, it would actually find its way configuring this out. All right. So that's the Ising model. So we now have a bridge, okay, from the principle of minimum energy to quantum mechanics and a tool that will show us the combinatorial problem of this Hamiltonian. Okay. So there is a bridge. Okay. Okay, try to put that in mind that we now have a way from a combinatorial optimization problem, which is the one and zeros, in this case, up and downs, to representing it into quantum mechanical states. That means we can simulate this problem already in quantum mechanics, hence on a quantum computer. So this is a way for us to translate, okay, your real world problems to a quantum computer by translating it to the Ising model. So the Ising model actually looks like this as a mathematical representation, wherein we have this part right here. This is your sigma I. Sigma I is really just the external interaction at one point. Okay, so acting upon one part of the particle right here. And then there are interactions. What if this part right here spins up, or sorry, this one spins up and this one spins down? What would be the interaction? Okay, what is the value of that interaction if we have them? So that is part right here. So take note that these sigmas now are the decision variables. So if there's only a single sum of a decision variable, of this binary decision variable, it is linear. However, this part right here, we're multiplying okay, two binary decision variables, which makes it quadratic in nature. So from here, from this easing Hamiltonian, we have a way now to translate it as a mixed integer quadratic program, an MIQP. Okay, we have binary variables, which are the integer part, but we also have quadratic, okay, because there are interactions of these variables. So it's now a quadratic program. So it looks like this if we try to arrange it as a graph. Okay, see? So there are interactions and there are intrinsic values of your certain particles. And we can scale this later on. So if you can visualize it as a graph like this, that means other graphs that also looks like this could be translated as an Ising model, right? And what other graphs looks like this? Some also can form a spanning tree. Okay, Hamiltonian cycles, similar to the traveling salesman. Distribution networks may also look like this kind of graph, right? So that means those problems those are quantum applicable as well. So there is the Kubo model right here. So this is now another stage for us to represent, because -1 and 1 are not really natural for us as binary variables. 0 and 1 is. So we're just going to translate that into what we call a quadratic unconstrained binary optimization model, or a Kubo model. Okay. Q is not quantum, by the way, it's quadratic. That means this is still classical. Okay. This is a classical model. It's just a translation of this, okay, quantum expression, or nearly quantum expression, to a classical or purely classical one. Okay, so we're really going up level to the classical level here, but there is that transition. Okay, so it looks like this. Okay, the minimization of some y is equal to x, all of the interactions. If you have 10 different variables, that's 10 different values of x multiplied to a q. This q is all of those values. These could be the intrinsic values and the quadratic values of choosing one and both, or pairwise. This lambda p here is actually the representation of all of the constraints that you could put in here. Instead of having subject to constraints, we're actually using it as an unconstrained form, wherein we have penalties, or p. So it now becomes part of your optimization model. Okay. So that's a way for us to convert all of your regular math to something, to a math form that is familiar to quantum computers. So it looks like this. There is a mixed integer quadratic program, or a general mathematical problem. We convert it to a Kubo problem, then to an Ising problem. And from the Ising model, it could now be run in quantum computers. It could be using an analog quantum computer. If you want to run it on a digital quantum computer, we just need to change the Hamiltonian that we know is an operation onto a quantum system into a gate, or let's say a quantum circuit. So there is that sense. That's the theory behind all of this and how we can actually use it. So we have a problem, we have objective. Now let's talk about the quantum method. So it's quantum optimization. So we have different quantum computers, by the way, but if we remember the Vincenzo rule, or the Vincenzo criteria, we have universal quantum computers. Those that could be measurement based, that could simulate adiabatic processes. Okay, all of these are here. So the UQC, or the digital quantum computers in this case, are universal quantum computers. They could be measurement based quantum computing, adiabatic quantum computing, and topological quantum computing. But not all quantum computers do these. Okay, some of example, for example, superconducting qubits, neutral atoms, trapped ions can perform gate array computing, which are under or could be in the subset of universal quantum computing. However, which are not part of them. Okay, quantum annealing. Okay, so trapped ions. Okay, if they're not performing gate-based computing, could not be universal quantum. There is another one right here in adiabatic quantum computing. Um, they could be used. Neutral atoms could be used to run these, but not all quantum devices or computing devices could be used. For example, quantum annealers. Quantum annealers do perform adiabatic computing, but they could not they could not perform any gate-based optimization. Okay. Topological quantum computing could be also anion braiding or Majorana fermions, similar to Google's chip. Okay. So let's look at, what's going on right here. So we now have the Schrodinger's equation. Remember that the Schrodinger's equation is just a way for us to describe the energy of a quantum system. But what we have discussed so far is just, without looking at time. But if we now have the OG, Schrodinger's equation, we need to consider time. So I'm just going to work on the math here, and it looks like this. The time evolution of a quantum object looks like this. That means the characteristic of your operation or the energy configuration of a quantum system is based on the change. Just don't mind all of the other things here. This is just change. And this is a change in time. Okay. So if you're familiar with your calculus, this is just a change in time. So that means there is the change of time of your quantum system. It does look like, it will form eventually into your quantum operation, okay, of your energy configuration. And if we want to, isolate the value of your quantum system, it looks like this, okay? This E raised to IHT. And this is the representation, okay, of the time evolution of the Hamiltonian onto your quantum system. And we're going to go back a bit here. That means there needs to be an evolution of your Hamiltonian so that you'll get the minimum energy. Okay, that's the gist. There are other ways. There are many ways to do that. For example, quantum annealing is a way to do this. You just need to prepare your magnetic field so that from a higher energy state to a lower energy state, we are going to anneal the process so that the Hamiltonian will naturally fall into place and finding the minimum energy. For example, here. So we just need to define an initial Hamiltonian at the end of this adiabatic computing. We're just going to prepare your initial Hamiltonian. It will evolve over time, okay, so that we'll be finding the minimum value. Okay. So an advantage of quantum annealing or the adiabatic process in general is it can tunnel from local minima to other parts of your system. So that is the quantum tunnel. That's the quantum effect that does not exist, okay, in other classical optimization. So being stuck in local minima is a very big problem, for example, in gradient-based optimization, because it needs to do a numerical jump from here to here to find that space. The alternative of doing this is really having multiple candidates or multiple options. So for example, in meta heuristics, this could be solved by throwing out random particles and exploring different options. While in this case, in quantum annealing or in the adiabatic process, it could actually perform tunneling in other local minimas. So like this. So for example, here, so given your initial state, it will fall into this final state right here. Okay. So initially it will it will just be certain particles, and across time, eventually it will find out this proper configuration. So right here, S is the steps or time. So from the initial Hamiltonian, we're going to evolve it until it becomes the final state. Okay, so I'm going to show you some things that we have done for quantum optimization. So for example, we use it for urban planning. So it's one of our examples right here with our friends from Adamson University, we are looking trying to find which places would be good to place sensors. So we have a formulation. This is your mixed digit quadratic program, and it could be converted as a Kubo problem. And this Kubo problem now could be run on a quantum computer, and it solves these problems. So all of these stars are the or the optimized locations. Where should you put a certain sensor? Okay, so that's one example. Another one is we use it for optimizing power systems, so that if you want to minimize, okay, the cost for operating all of our generators so that you won't have any brownouts, we can actually use this for creating a good schedule of all of your generators. Okay. We also used it before in computer vision. How do we, if you're familiar with non-maximum suppression, it is the algorithm of choosing all of the good boxes in object detection. Okay, and that is actually a combinatorial problem. So you can actually express the non-maximum suppression as a Hamiltonian like this. That this is actually just your Kubo problem right here. Okay, so those problems exist everywhere. This is not highly specialized, but these problems are out there, and we just need to translate them to something that could be, okay, applicable to quantum. So it's good if we can use it in quantum, but again, not all problems could be converted to quantum, for example. What are problems that we could not convert into quantum? Generally, anything that requires you to have a continuous variable. Okay, so if the decision variable that you're trying to solve is you need to have, for example, specific decimal values, for example, temperature, time, or what is the optimum time for us to solve this issue, or time to create things or manufacturing problems such as that, or exact numbers of volume, then those are concerns that could not be solved in quantum. Okay, so that is still best run on a classical computer so far. Okay, so let's try to make this. So I think I hope I have time because I do have some examples of how we can do this in code in Qiskit. So let's try to do this first in the theoretical aspect. What are the steps? Okay, what are the general steps? So here I'm going to introduce to you the concept of the quantum approximate optimization algorithm, or QAOA. So this is the digital quantum computing version of quantum adiabatic process of finding the answer to the minimum energy, the principle of minimum energy. How do we translate, okay, the energy configuration solving of an Ising model in the Schrodinger's equation in a digital quantum computer using everything you know so far about quantum circuits. So essentially, it's like this. It's just really stacking multiple unitary operations to your initial quantum system. Initially, this quantum system, of course, is either in superposition state or in the zero states. So each of them are called problem unitaries. So these are the encoding. Okay, if you remember earlier, these are the encodings of your Hamiltonian. That means we're just really converting them as a quantum gate or a quantum circuit. So we also have mixer unitaries. Mixer unitaries are parts of your quantum circuit that allows you to search, okay, multiple values, or explore different values. They help in the entanglement and the quantum annealing, sorry, not, the tunneling process of searching answers. So we call them, well, a problem Hamiltonian and a mixer Hamiltonian. So the problem Hamiltonian includes all of the things that you're considering for optimization. For example, your objective function is in the problem Hamiltonian. A mixer Hamiltonian is altogether a very different quantum circuit. Just you need to design so that it will search proper values. So from your time evolution Schrodinger's equation, we can actually convert this into a QAOA problem. So from your time evolution of a quantum object, it looks like this. Remember, it's just a change in time, and you have your Hamiltonian. And it looks like this. Remember that it looks like your unitary problem. So if we could stack that time step of the change of Hamiltonian, it is just really doing it step by step. Okay. Instead of having it a continuous time, we are doing this at every stage of the optimization or change. So this concept is actually, a digital version, and the concept behind it is called trotterization. Okay, so and for those who are practicing signals or those in engineering or might know this, that the approximation of a smooth function could be represented by individual line segments, right? So if this is a very cool, very smooth line, that those are 1,000 points in approximating them, that's cool. However, we don't have, unlimited resources in quantum. For example, each of these Hamiltonians or unitaries would take up your circuit depth. And we cannot have an infinite size of a circuit depth because we only have very short coherence times for some quantum computers. So we want to lessen the amount of these stacks of operations, but still have the right answer. So that is a concern of digitizing certain smooth processes. So imagine your adiabatic process or the time evolution is smooth, but in a quantum or a QAOA problem, you need to find the discretized version, but yet approximating it properly. For example, using 5 points to approximate this smooth function right here would not be enough, but probably 15 points or 10 points would be just enough depending on your problem. So that talks about the circuit depth of a quantum or a QAOA problem. Okay, we cannot really have an infinitely large QAOA problem in this case, or deep QAOA. So here, this is just really stacking of your quantum optimization. So there is a pattern. You have your problem unitary, then mixer unitary, and you have you're just going to repeat that process, simulating the time evolution of your Hamiltonian. Okay. So the QAOA problem or QAOA algorithm is actually a VQA or a variational quantum algorithm. So similar to what Edmer discussed previously, it is something like that. Okay. So what are the things? Because all of these Hamiltonians before, they have, okay, parameters, okay, beta and gamma. So beta and gamma are rotations. Okay, these are rotations that would define the proper or the smooth transition of your Hamiltonian states, okay, your Hamiltonian evolution. So we want to find out what are these values of beta and gamma, and these could not be immediately solved in a quantum computer. The quantum computer could solve the finding the minimum energy problem, but it needs to have the proper configuration of your quantum circuit. So we need the help of a classical computer. So that's your classical optimizer. So what happens is that I run the quantum computer first. It gives me an answer. Now, is the answer the lowest possible energy state right now? If it's not, then I might need to change my beta and gamma so that it could give me a better solution. Okay, so it's an iterative process until we find the best values of beta and gamma for the quantum optimizer, but the quantum optimizer is really the one finding the right answer given the principle of minimum energy. Okay, so it's like a two-stage optimization problem. Okay, so two things we need to consider here. There is quantum annealing and there is QAOA. Please do not mix them up. Quantum annealing or the quantum adiabatic process is not universal quantum computing. That means you cannot run a quantum annealing process on Qiskit. You cannot run it in a Rigetti, in IonQ. All of those. You cannot run quantum annealing in that. There are very specific ones. For example, D-Wave does quantum annealing process. The adiabatic or AQC adiabatic quantum computing that could be run in using neutral atoms. So, for example, blockade by where's for yeah, I forgot. Remember, I forgot that. But yeah, so we have blockade for you to create your. Oh, sorry, QERA. QERA is the platform for running neutral atoms for adiabatic quantum computing using specifically analog blockade. So these quantum annealers are not robust to noise. Okay, so they are very highly subjected to noise. So what they do is they just create more qubits and just estimate based on their guesses. Okay, the QAOA is a gate-based quantum computing circuit. That means there is a quantum circuit for it. So it's good for universal quantum computing. However, it uses mixer and problem Hamiltonians. We need to have those conversion, and there is a resolution problem by trotterization. That means we need to downsample the number of steps to correctly characterize the quantum evolution process. Okay, and it is a variational quantum algorithm. That means it needs a classical computer to function. Okay, quantum annealing does not require a classical computer, but it's very robust to noise. Sorry, not robust to noise, and it would just directly use a Hamiltonian. Okay. However, these are very specialized ways to do it. Okay. That means you're not going to use any gate-based quantum computing. So let's try to, sorry, not traveling salesman. Again, this is knapsack problem. We're going to do something. So this is a general TLDR, I guess, for everything that we discussed so far. From the class, you can actually program just in the classical sense, and it will be solved. Okay, it will still be solved by a classical computer. The answer will still be correct, most likely. Okay, but it might be slow if we try to scale the problem. So if it's an MILP or MIQP problem, you can use CVXPy or MOSEC if you're using in Python. You can just run that. You can model and simulate them all together. Okay. However, if you want to follow the quantum way, so first, you need to convert your MIQP or your classical mathematical problem into a Kubo model, okay, here. So you can use Fujitsu's AutoKubo if you want to do that. You can also use OpenGIG or GIG modeling. That's something in the tutorials that we have. So you can convert that using in that way. And so once you have this Kubo to easing form, you can actually simulate it using simulation. So there's simulated annealing. There is also what we call simulated quantum annealing. So if you want to, if you don't have access to quantum annealer, you can actually use a simulated version. Then we need to convert that, okay? So how can we bridge Kubo to QAOA if you want to work on a classic in your for example Qiskit or any gate-based quantum computers. So we need to convert your easing model to a Hamiltonian or sorry a unitary. So how do we do that? So we can use several ways. You can use the mathematical version that we're going to see in a few slides. However, there is a package already in Python that helps you convert a Kubo instance or a Kubo model directly to a QAOA circuit. That's called Chamomile, and we're going to use that in a tutorial if we can have it in the next few moments. So once you have them, you can now do a QAOA. You can now perform QAOA, okay? And you can simulate it using Qiskit or even in CUDA Quantum. If you're interested, Qiskit can actually convert directly from an MILP problem directly to a QAOA. However, I think that's in the very previous versions of Qiskit, but I think it still exists, so you can also try that. You have a full stack in Qiskit converting from a classical mathematical model to a QAOA to simulation. But if you're using GPUs, then you might want to look at CUDA Quantum, so you can use that as well. Or if you're using a different quantum computer, such as Rigetti, QERA, sorry, not Rigetti, just not QERA, just Rigetti and IonQ, you can opt for using Chamomile for that conversion. So let's try to go through these step by step. So let's first define the problem. So we're gonna do the knapsack problem at the fiesta. Okay. So the knapsack problem is that given a set of items, each will have a set of weights and values, and you're given a container with a limited capacity. So the problem is how many of our items or which of those items should I select so that I can maximize its value, okay, but within or without exceeding the capacity. So let's say I'm at the fiesta or I'm at the party and my mom gave me these containers, these Tupperwares, and I am allowed to take home any of these four items. I could take home a barbecue, lumpiang Shanghai or spring roll, rice, or the CD of Sharon Coneta. So those who know, you know. Okay. So I have these four items. Which should I take home? So given the capacity. So some say I could take them all or just hide my lumpiang Shanghai at my pockets, but no, let's not do that. Let's just stick to the Tupperware. So that's the problem. Now let's try to convert this problem into a mathematical sense. So here it is. This is how would you take home your Sharons, your takeouts. So the decision variable is X. Should I take this item home or not? To be or not to be, that is the question. So these are items 1 to n. So I have 4 items. So I have x1, x0, x1, x2, and x3. So I have x0 for choosing Shanghai, x1 for choosing barbecue, x2 for choosing rice, and x3 for choosing Sharon CD. So they have a value of 8731. Okay. These values could be the likability of my mother from these items right here. So probably or my family at home. So let's say the highest priority right now is Shanghai. Okay. So 8 is Shanghai. Barbecue is a value of 7 of interest for people. Rice is just free. Probably there's rice at home. Or CD1. Like who wants to have a CD of Sharon? Unless you know your mother is really an avid fan. And let's say the weights in grams would be like this. So there are 20 grams of CDs. That's a lot. There are 40 grams of Shanghai. Very limited, probably very few left. There's still 200 grams of barbecue and 100 grams of rice that you could take home. Okay. So given that, let's choose. How can we choose that? So the objective function here, or my objective is maximize value by, however, keeping the weight in check. So I need to choose which of these would produce the highest value or the total of highest value, but not exceeding the weight capacity. Okay. This could be not weight, it could be volume if you want, but let's say it's generally capacity. So we can model it as this. So V is value, W is weight, X is to choose or not to choose. The big W is your maximum weight. So let's say it's 300. Let's say it's 300 or so. Okay. How could we? Which one should we select so that we can fit until the 300-gram limit of my container, but yet having the best value of all the things that I have? All right. So how do we make it combinatorial? So it happens to look like this. So if we're going to convert it to a Kubo model, it has to be combinatorial. So if we only just consider each of these values, each choosing just one of them and the values, that's linear. That's linearity. But if we consider the value of choosing them together, and they might increase values if they're a pair, or the likability of that of my likability of those items, considering my parents or considering your brothers and sisters. So let's say it looks like this. If I only choose Shanghai or my lumpia, okay, it is the interest of that or the value is 8. If I choose Shanghai and barbecue, the interest is 10. Okay, that's a lot more. Okay, that means people would like it better to have those together. If I choose rice or Shanghai with rice, it becomes an interest of 11. If I choose Shanghai with my CD, it's just 2. Okay, like who wants a Shanghai with a CD, right? So we have that. Okay. So next would be let's have you have all of these combinations. Let's say I have Shanghai barbecue with rice, barbecue with a CD, if that's your thing, right? So let's try to look at it. Right? These are the problems. So if we want to optimize, so it now becomes a combinatorial problem because we consider the pairwise impact. If there are no pairwise impact, this is not a quadratic problem. It's a linear problem. Okay. So in this case, we want to have this combinatorial sense. Now, these purple values are considered quadratic because they're pairwise. That means we choose them together. Okay. So this now looks like your value matrix. We call this a value matrix. Next. So how do we look at this as a Kubo model? So given this matrix right here, it has this form. This is a Kubo form. We have a linear form, okay, the linear part and the quadratic part. That is the formula of your Kubo. We're trying to maximize, okay, the choice of choosing one as an individual, okay, but also considering the choice of whether we choose another together with it. That's why we have Vij with Xi times Xj. That means when we choose, for example, Shanghai and barbecue, what will be the value of V? That's 10. Okay, so given all of those combinations, which combinations would give me the most value? Okay, all right. Note that for this problem, xi times xi is equal to xi. Right? Why? Because, for example, xi is 1, and let's say that's x0, choosing x0 and x0. 1 times 1 is 1. 0 times 0 is 0. It's always that case because it's binary. Okay? It's only for this problem, okay? In Kubo problems, if you multiply them together, they're still the same. All right. So this for this problem, xi times xi is equal to I. That means xi squared is equal to xi. All right. All right. Hope you get that. Now, but since Kubo models by default are minimization problems, we need to convert. See what happened. From maximization, we need to turn it to a minimization problem. We just need to turn it to its negative side. So the maximum, okay, that is an optimization rule. So the dual of this problem, or what the equivalency of this problem, that if you want to maximize something in the positive form, you just want to minimize it in its negative form. Okay, we need to find the minimum value of your negatives right here. Okay, right. So that's the minimum. That's the minimum form. Oh, sorry. This is the easing form, not the Kubo form. From the Kubo to the easing, it would look like this. There is a formula for that we're not going to go through with this, but this is the value of your easing model. So if we want to convert this to a QAOA model, we would pertain to this part right here. Note that is easing. Next, simulation. Simulation could be done classically using simulated annealing. So you can use PyKubo, OpenGIG. Quantum annealing, however, at this point, because since you only have an easing model, you can only use it for a quantum annealer. You can use D-Wave for this. Okay, if you don't have anything else, if you want to use digital quantum computer, you will not stop at this step. You'll not start. You'll not stop at step 4. Okay, you need to proceed to the other steps of conversion. But if you just really want to work with quantum annealers, then you stop here, right? As long as you have your easing model, you're fine. But let's say we don't. It's not enough. So we need to convert. So in converting the QAOA problem, we need to consider your easing model. How do we really convert it to a specific Hamiltonian? So given your easing model right here, these lines or this diagonal, sorry, this is not, yeah, anyway, let's say here it's 0 as of the moment. So the RZ will be dedicated to this rotation right here. So an individual gate pertains to a linear option of just choosing one. However, if you are choosing binary, or sorry, in a pairwise manner, you need to have a ZZ gate. So this becomes a controlled Z or a CZZ gate. So in this case, you need to consider two values at the same time. Okay, so that becomes this weight right here. So that becomes the interaction between these values. Actually, there is a sense of entanglement within these. That means you're entangling two qubits at this point pertaining to choosing rice and barbecue. So imagine you have a qubit for Shanghai, a Shanghai qubit, a barbecue qubit, a rice qubit, and a CD qubit. Those are your options. So each of these would pertain to your qubit. Okay. So if I have a 4x4 matrix that's 16 different combinations, that you still need 4 qubits. Sorry, yeah, 4 qubits, not 16 qubits. Okay. So in this case, if we're not considering any slack variables, okay, we only need 4 qubits, right? Not 16. So in this case, you can formulate this as such. So if you want to convert, you don't want to convert it manually, you can always use Chamomile. Well, you can just use its APIs to convert your easing model directly to a QAOA circuit. So there are other things. So let's say you already finished your problem Hamiltonian, you just abstracted as HP, but there are other options. So you still need to create your mixer Hamiltonian. So the mixer Hamiltonian allows you to explore other values, or that's why simulating tunneling and others would use it for enforcing penalties. So you can also use that. So for example, the X mixer right here is the most basic mixer Hamiltonian. There's the alternating operating ansatz mixer, wherein you have customized unitaries for every combination. And there's also XY mixers, wherein you can use combinatorial XX and YY gates specifically to the interactions that's needed. So that research is actually made by Google, so you can actually look at that as well. But for the examples, if we do have time, let's use the X mixer. Right. In digital simulation, again, easing models in Kubo are good for annealers. So Fujitsu does have a digital annealer and D-Wave has the quantum annealer. But you can never use an easing Kubo directly on a digital quantum computer because that's not the hardware. That's not the hardware it does. Okay, that does the instruction set is not the same. Okay. However, if you're using QAOA, you cannot run a QAOA on a quantum annealer because that's not the instruction set it's made for. Okay, but you can run it on a digital quantum computer. Okay, so please don't mess this around. So if you have QAOA, you don't have to use quantum annealers. Use a digital quantum computer. If you have an easing model or a Kubo problem, a Kubo, you can directly use it on an annealer, but you cannot directly apply it to a digital quantum computer. You need to convert it. So this would be the most advised way to run these. So you can run using your annealers with a Kubo or easing model. But if you're running on a QAOA, please use a digital quantum computer. So that is it. However, do we have time? I just want to check with AD. AD, do we have time for a
Yes,
demo?
sir. Meron po.
Great. Very cool. So just requesting the team for sharing the link. So let's share the link number 1 first. So let's run a quantum fiesta. Right, cool. Let me just share my quantum fiesta right here. Oh no, where's my quantum fiesta? So this is the weirdest fiesta I've ever been. Okay. Wherein we use quantum computing to take home my lumpia. All right. So I already have some files here. I'm just gonna restart this. So let's run our quantum knapsack problem at our Fiesta. Note that we are not going to run on any quantum computers right now. We are just running on simulations. But we are going to go through with several steps. We're going to go all through steps 1 to 4 at this notebook. Okay. We do have a separate notebook which we have right here. If time permits, let's try just going to run this here. All right. So first things first, please open the notebook. Then you need to uncomment the setup. We don't need these libraries right here. We need a CVXPy. This is your classical optimization algorithm. Jig modeling would be used for modeling your quantum your Kubo. Then OpenJIG for simulation. We do have adapters here just on conversion, but that's not much of an importance right now. Right, so we're just gonna have these. So again, we have our items. We have Shanghai, barbecue, rice, and CD. Okay, Sharon CD. N would be the number of items that we have. Weights would be the weights that we have earlier, and the maximum weight, okay, of 300. We have our value matrix from the table that we had earlier. So you have 8, 10, 11, then 2 to 2 here. So this would be Shanghai barbecue rice CD, Shanghai barbecue rice CD. Okay, let's zoom that a bit. Let's run that. And we have, oops, what's happening? So here we have your value matrix, okay, and your weights right here, maximum capacity. Next, we'll just have a helper function on the evaluation. So once we have your vector, that's going to be binary strings. So it's going to be, the choice would be 1101 or 1111, 11111, or 1110, something like that. So that will be the indication of which do we select. So if it's 1110, that's Shanghai barbecue rice, no CDs. But if it's 1111, that's everything. 0111 or 0110 is barbecue rice, no Shanghai and no CD. Sad. Okay. So let's run this. That's your helper function right here. Then I'm just going to run CVXPy. Given our formulation, we're not going to go too much deep into the mathematical formulation, but this is how we do it. Okay. So the classical baseline would be Shanghai barbecue CD. Okay, Sharon got the hit, right? So in the optimized version, the maximum value of just having 260 over 300 capacity, we have Shanghai barbecue and CD. Rice did not make it. I'm so sorry, Rice. Probably there's rice at home. So in this case, the optimal configuration using the classical method is we need to take home Shanghai barbecue and CD because that gives the best value while having it in the weight. Okay. Why did we have a CD? Probably Shanghai barbecue together has the highest value, but if we add more, if we add the rice, then the weights will be the weight will be maxed out. But CD just gives that space. So if you are not really that much into Sharon Cuneta, then you can leave the CD, but that will not give you the maximum value. It's still a feasible answer. Okay. Anyway, so that's the solution. So let's try to convert this MIQP problem into a Kubo problem. So to we do that, we need to do it a bit manually in this case. So we need to formulate this in JIDG modeling or JM. So that first, let's define the knapsack fiesta. Okay. Then we just need to define the diagonal parts, which are your linear terms, your quadratic parts as diagonal or pairs. That's A and B. Then we have your weights, your maximum capacity, and the number of items. We only have one decision variable, that is x. I and j will just be the indices of your diagonals. Why do we need that for going through all the options in the products and sums? Okay, so in this case, so let's try to we're just gonna declare the upper triangular, so that would be the combinations. So the problem would be first the sum of the diagonal parts, that is your linear part, then the upper triangular, okay? The upper triangular would now be your, the upper triangular is the combination parts. Then we just add a constraint right here. You don't have to manually solve the penalty conversion. So we just add it like this. So if you have your constraint right here, that is the sum of the weights of the chosen ones should be less than the maximum capacity, which is 300. So if you run that, the will have this rendered part right here of the Fiesta knapsack, and we have this your optimization problem. So this is done by JIDG modeling. So that helps you to characterize your problem. Okay. Next, just have your instance data. That means this is the characteristic of the problem. Okay. Then once we have that, we're just going to convert it to the Kubo matrix. So the Kubo matrix will always have your offset and your Kubo. The Kubo would be the nominal values. Offset would be the maximum values that would could be factored out, or sorry, added out, so that it will become in the nominal value case. So this is your Kubo JSON, right? Or sorry, this is your Kubo matrix actually here. So we have 0, 0, 0, 1, 0, 2, 0, 3, and that would give you your Kubo matrix. You can actually plot it if you want, but right now that's not the important part right here, right? So we can save this for later since we want to do it in QAOA. So let's just get JSON, then let's just export this right here. So if you have that, it will be right here, your Festa Kubo. There's party right here, but that's the old one. So that's it. That we already modeled. That's already steps 1 to 3. Right? It's quick, right? Next, let's try to simulate it using the simulated annealing. So I imported from OpenJIDG my simulated annealer sampler, simulated annealing sampler, and the simulated quantum annealing sampler. Okay. So the number of reads, that means how many times do I need to generate my quantum scenarios and get the average value. That's the number of reads. You can do 1,000 if you want, okay? But 100 is all we need. So we just need to instantiate your sampler right here, simulated annealing. Then we're going to sample our Kubo, okay? That means we're going to subject our Kubo or using model in this case, right? Then we're just going to get the best answer, which is the first, okay? And it will give us our answer. So if you run this, that's quite fast. So the answer is Shanghai barbecue CD. It is consistent. That means our Kubo formulation is correct. Okay, that means the conversion from the classical mathematics to the quantum mathematics is same. Okay. So that is a very good validation check for you. If you're converting your mixed integer linear problem or quadratic problem from the classical version to a quantum version, this is a very good step, even though you're not accessing a quantum computer yet. This is the math that needs to be run on a quantum computer anyway. So good way to check what's going on. Okay. So sanity check, that's correct. So Shanghai barbecue CD is also validated by your simulated annealing. Next, if you want to simulate quantum tunneling, then you might need to look at simulated quantum annealing now. For now, it doesn't really make sense because our search space is quite small. That's just 4 items. But if you want to scale, for example, with 100 items, 1,000 items, then you will produce a lot of local minimas. So if you have local minimas, that means your problem is prone to be stuck in certain answers. So we don't want that. So if you want to get by that, or get out of your local minimas, then you need to simulate quantum annealing. So you can use SQA. So to do that, you just need to instantiate your SQA sampler, then similar things. Just run the Kubo and get the best answer. And the answer is the same. Okay. So the answer is still Shanghai barbecue and CD. So right now, there's really no difference between SA and SQA, or simulated annealing and simulated quantum annealing, because it's quite the problem space is quite small, right? Comparison. Let's try to run this comparison right here. As we see it, they're all consistent. That means they're all feasible. That means they did not violate the constraints that we have. That's another consideration. Right now, we're lucky that it is feasible, but in sometimes, if the problem, the formulation that you did is not really that good, you will face infeasibilities for multiple constraints. And we don't want that. That's not a valid solution if we invalidate or certain constraints, right? So that's something that we need to consider before we move on in trying out to a real quantum computer. So this really checking whether your answers are correct. Okay. Let's try to visualize that. Well, anyways, they're just the same anyway. So they will just look at, see like this. Okay. So their weights are just near the maximum capacity. That's really fine. So yeah, they're just the same. This is a good sanity check actually for running this. All right. Before we proceed, I'm gonna check some questions. 3 minutes left or no? So just for the others, I think you can check. I think the guys here can check, or sorry, can send QAOA number 2. Okay. So the second part right here. I'm just gonna skim through this. I'm not gonna run through, but the guys can share this so you can run it at your homes. So what is QAOA? Already discussed what's QAOA. So it's really just the digital quantum version of your quantum annealer, or quantum adiabatic quantum process. So I'm gonna skip to the part where it's quite very important to notice, is that first you need to deduct the offset. That's a very key move whenever you're going to use a saved Kubo file. Make sure that it is deducted from your offset, because those numbers are quite large. So that will hurt your optimization. You're going to get suboptimal problems, suboptimal solutions. Okay, that's one. Next key step is that you need to use OMMX to convert it from Kubo. So in this case, use a binary model. So you're going to convert your Kubo model to a model that will be used in the QAOA converter. Next, you need to perform normalization, this step right here. So some of the values might be too large for the scale, so you need to normalize it in any way. It could be the maxima or RMS, root mean square, or the Frobenius norm, if we call it. Okay. Then from there, you can get a cost Hamiltonian. And that now is now your QAOA circuit right here. So you can use a Qiskit transpiler now to convert this model. Okay, so this model is already compiled right here using 3 steps, or 3 layers of my quantum, or 3 layers of my QAOA. Then you can run it by using your Kobila right here. So this is just using SciPy, by the way, and your AER simulator. Then we can minimize your cost function, which runs your circuit. So initial parameters are your beta and gamma. We want to find that, what gives a very good quantum optimization flow for this. And if we look at that, if you look at the convergence plot right here, it actually converges around 30. Okay. Then for the optimized parameters, we're just going to input your optimized beta and gamma, and it should give you the results. And it should make the optimization of your quantum circuit, well, optimal. So the answers here will still be Shanghai, barbecue, and your CT, right? So in this case, it's what happened. Okay, that means the answer is consistent. That's the first check. Whenever you're doing quantum optimization, make sure that the values are same. They are all feasible, and they are, well, just near the values, or even sometimes better than the classical benchmark. But the basis is that there are no constraints violated. That's one. So we're not going to run all the comparisons for all solvers anymore, but in this case, that's it. So um, I think that's all for the optimization part, so we can have more questions for everyone. Great, thank you.
Thank you, Sir Dylan. Okay. I think we don't have much time, sir.
All right, okay.
But yeah, if if you guys
This
have
is a
any
great lecture.
question,
This is a
yep,
great lecture.
thank you. If you have
I
any
enjoyed
other
it.
questions, you can just ask in
No,
the Discord server. Yeah. Thank
it's
you.
basic. Yeah, I will ask. Thank you.
For our final announcements for this class, yeah, we already have an assignments for you guys, so we already posted it. So you can just log uh in this learning management system that we created. So try to log in and then just put your email. I think some of you have concerns. So if you have any other concerns, like you cannot log in, just let me know. I'll try to solve that. And then, yeah, we already posted assignments for Module 2 and Module 3. Now, for Module 4, it will be follow. For Module 5, let me check if we can create further assignments. Yep. And then another thing that we want to discuss, we're going to celebrate World Quantum Week next week. So April 14 is the start of the World Quantum Week. We have some events prepared for you guys. First, we have disengagement events. We have Quantum Myth Busters and Professional Spotlight. So for Quantum Myth Busters, these are just postings about the current myths, debunking the myths in the quantum field. For Professional Spotlight, yeah, we do have some Filipinos working in the quantum field, and we want to spotlight them. Yeah, just check our Facebook page, Quantum Computing Society of the Philippines. We also have some events like QB's Intro to Quantum. So this is like a lecture series, but it's just for one day. It's just a summary of introduction to quantum computing. So if you want to review some concepts, I invite you to attend. So just wait for the announcement in our page. We also have talks and webinars to follow after that introduction to quantum. And we also prepared some competitions for you guys. We have XQBit. So this is an external event. So the one that we announced for you guys, internal XQBit, is the one internal for our lecture series. So we created an XQBit for all the participants, not just for lecture series. So if you already created your XQBit project for this lecture series, you can submit it to them, and then let's see. Uh, yeah, we also have QuizBit. So it's like a quiz B for quantum topics. And we also have Circuit Crunch. Yeah. If you think you are an expert in building quantum circuits, then I invite you to join Quantum Circuit Crunch. So this competition is you have to transform a certain equation to a quantum circuit. Yeah. And then, yep, and I encourage you guys to visit this website, create an account, register there, and then all of the registrations will happen on that website. Yeah, I think that's all for tonight. Thank you, Sir Dylan. Thank you, Sir Edmar, for giving us a talk and introducing us to these concepts in the quantum computing field. Yeah. Thank you guys for attending. Thank you, sir. Thank you. If you have any questions, like you can ask it in our Discord, and then I will relate to Sir Dylan or Sir Edmar. Thank you.